Hello, so today we're going to talk about L'Hopital's rule. And the first thing I want to do is to remind you of what we call indeterminate forms. Okay, so we talked about this a little bit when we first learned about computing limits. And let's look at this first limit here. So let's see here. So the first limit is, what's the limit as x approaches 4 of x squared minus 16 divided by x minus 3. My first line of attack is to plug in x equals, it's to just plug in x equals 4. And then I can say, since the function x squared minus 16 is nice enough, right? It's a polynomial, so it's continuous. So the limit as x goes to 4 of x squared minus 16. The 4 that's just going to go to 0, right? Because the x goes to 4. So you'll get 4 squared minus 16. So the numerator goes to 0. And then the denominator is going to approach 1 as x approaches 4. So we can say, since the numerator approaches 0 and the denominator approaches 1, our limit is equal to, in fact, let me just erase here. Our limit is equal to, it's going to be equal to 0 over 1, which is equal to 1. Okay, so this limit is equal to 0 over 1. Sorry, not as 1, is equal to 0. Okay, let's look at our second example. So here we've got the limit as x approaches 4, and I'm going to do my same trick. I'm going to say the numerator is continuous, the denominator is continuous. The numerator approaches, what is this? So as x goes to 4, so as x goes to 4, x squared plus 5 is going to approach, what is that? So it'll be 21. And the denominator, which is x squared minus 4, is going to approach 4 squared minus 4, which will be 12. So this limit is going to be 21 over 12. Is equal to 21 over 12. Now what about our third one here? Here we run into an issue. If we try to just plug in x equals 4, sure, the numerator, x squared minus 16, is going to approach 0 as x approaches 4. The denominator is also going to approach 0. So x minus 4 approaches 0 as x goes to 4. And remember, because this limit is of the form 0 over 0, it's not equal to 0 over 0. So let me remove this equal sign. So we'll say is when we get this 0 over 0, this is one of our indeterminate forms, right? So one of our indeterminate forms was 0 over 0. Let's look at this last little example here. Now again, as x approaches infinity, so as x approaches plus infinity, what will happen to 4x squared minus 5x? It's going to approach plus infinity, right? Because the x squared, 4x squared minus 5x looks like a parabola, right, facing upward. So it might be something like this, similar to this. Actually, it'll be something like this, right? It's the graph of 4x squared minus 5x. So as x is going to plus infinity, our function is going to plus infinity. And the denominator, 1 minus 3x squared, is going to be approaching negative infinity. So again, we have the form of plus infinity over negative infinity, which is an indeterminate form, right? An indeterminate form. So here's some other indeterminate forms. So if you have 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, negative infinity over negative infinity, these are all indeterminate forms. So we could actually wrap up all of these and just write this as plus minus infinity over plus minus infinity, right? So that'll kind of clean things up. So 0 over 0, plus minus infinity over plus or minus infinity. Another way we can get an indeterminate form is infinity minus infinity, right? Because you can't say infinity minus infinity equals 0, because it depends on the size of the infinity. Another one is 0 times infinity. 0 times negative infinity. That's another one. And then 1 to infinity and 0 to 0. And then infinity to 0. So let me say a little bit about this 0 to 0, because you might say, hey, wait a minute, anything raised to the 0th power is equal to 1. So why isn't 0 to the 0th power equal to 1? Well, that's usually true, right? So this is usually true. And the reason why it's usually true is because, say if you had something like 2 to the 0 equals 1, right? Then you can take log base 2 of 2 to the 0 would be equal to log base 2 of 1, right? And now that 0 would have to come down, so we'd have 0 log 2 of base log of 2 base 2 is equal to log 2 base 1. And we know that log 2 of 2, that would cancel out and we would just get a 1, so we get 0 is equal to log base 2 of 1. If we try to do the same thing with 0 to the 0, right? So if you try to say 0 to the 0 equals 1, well now we should be able to take log base 0 of 0 to the 0 and say that's equal to log base 0 of 0. But we know that we don't have a log base 0, right? So the log base 0 is undefined, as is log base 0 here is undefined. Why is it undefined? Because no number, 0 isn't the result when you raise a number to another number, right? So since log base 0 is undefined, that means that going back here, this 0 to the 0 equals 1 is also going to be undefined. Here's another way to see why 0 to the 0 is, or another explanation for why 0 to the power of 0 is an indeterminate form, is because, so on the one hand you can say, like we said before, anything raised to the 0th power equals 1, right? So you might think, yeah, it makes sense. But also, 0 to any power should be equal to 0, right? Because 0 multiplied by anything is going to be equal to 0. So 0 to any power is going to be equal to 0. So do you see where we get a problem? Do we say 0 to the 0 is 1? Is it 0? And because we're not sure what it should be, we call this an indeterminate form. So we'll actually get that sometimes when you take the limit, you don't get 1, you don't get 0, you get, some real number like 3. Okay? And our last indeterminate form here is the plus infinity to 0. That's also indeterminate. And this 1 to infinity, students lots of times get confused because they think, well, 1 to anything is equal to 1. But again, not necessarily, right? So we'll see some examples where if you have 1 and you're multiplying something that's close to 1 by itself a whole bunch of times, you can end up with something that's really big, right? Or you could end up with something that's really small. You never know. So we put all these forms are considered indeterminate forms. Okay, so far our techniques for finding limits are to factor and then cancel out. So let's show you on this first one here. This should just be a reminder. So for this first problem here, we want to find this limit as x goes to infinity. Remember, this is an indeterminate form, so if we just plug in infinity, we would get infinity over negative infinity, right? So it's indeterminate. Indeterminate form. So instead, the approach is to factor out an x squared in the numerator and an x squared. So if we pull out an x squared in the numerator, we'll get 4 minus 5 over x. And if we pull out an x squared in the denominator, we'll get negative 3 plus 1 over x, right? And then we're taking the limit as x goes to plus infinity. And now as x goes to plus infinity, 5 over x is going to go to 0. 1 over x is going to go to 0. The x squared cancels out, and we would end up with 4 over negative 3. So we say this limit is equal to negative 4 over 3. So that was our first approach, right? Techniques for finding limits when you have an indeterminate form was to factor and to cancel out. The second approach was to rationalize. Again, if we try to just plug in t equals 4, on the bottom here we would get a 0, and on the top we would get t minus square root of, this is with 4. What is sub t? So on the bottom we would get, so I'm just plugging in 4. So we get for t, 4 minus 4, and on the top we'd get t minus the square root of 12 plus 4. But t is 4, so we get 4 minus 4 over 4 minus 4. Definitely we have an indeterminate form. Okay, so again, how we would approach it, since it's indeterminate, is we would rationalize. So we'd multiply the top by t plus square root of 3t plus 4, and the bottom by t plus the square root of 3t plus 4. Okay, and then what would happen? We would get equals limit t is approaching 4. When we multiply the numerators, we would get t squared minus 3t plus 4. And then in the denominator, we would get 4 minus t times square root of 3t plus 4, and that's plus t. Okay, and now this numerator simplifies to, right, because that's t squared minus 3t minus 4. The numerator simplifies to t minus 4 times t plus 1. T squared minus 3t minus 4, right? So now this t minus 4 in the numerator and the 4 minus t in the denominator cancel out, and we're left with just a negative 1. So I'm actually going to do this all here. So the numerator, we're going to be left with negative 1, and the denominator, we get rid of that 4 minus t. And now we can just plug in our t equals 4, because we no longer have an indeterminate form. So we would get negative 1 over, was that the square root of 16 plus 4? So we get negative 1 over 8. Okay. The next approach that we have for finding limits when, this is for finding limits when it's in an indeterminate form. So look here, as x goes to 0, as x approaches 0, the x squared is going to approach, that's going to approach 0. And cosine of 1 over x, well, 1 over x is going to approach plus infinity. Or not even necessarily plus infinity, plus and minus infinity, depending on which way you approach, right? So this cosine, this limit is not going to exist because cosine is going to continue to oscillate between negative 1 and 1, right? So this limit is definitely indeterminate. It was not of indeterminate form. This limit simply just doesn't exist. So to help us out, we use, for a problem like this, we can't factor, we can't rationalize. That won't be helpful. So we just use the squeeze limit theorem. right? And remember, the squeeze limit theorem says if you can take your function and squeeze it in between two functions that you know are approaching the same limit, then you can find the limit of your inside function. So here we go. So we took our original function that we're trying to find, that we're trying to analyze. We want the limit as x goes to 0. Since the cosine function is bounded in between -1 and 1, cosine of anything times x squared is going to be bounded in between -x squared and +x squared. So now we say -x squared goes to 0, +x squared goes to 0 as x goes to 0. So this thing in the middle, which is squeezed in between, it's also called the sandwich limit theorem, because the function that we're trying to find the limit of is going to approach the same limit as those upper and lower bounds. So this also has to go to 0. So our conclusion is that this limit is equal to 0. And the last approach that we have so far, right, for finding limits, let me actually put in here, this is step 0 is limit laws. So remember, we have our limit laws, and there are several of them. And of course, we use our limit laws, and we especially use them on continuous functions, right? So that's our first line of approach. And if that doesn't happen, or if we can't use limit laws, we end up with something that's indeterminate. Now we go to these other approaches, right? Factoring, rationalizing, using the squeeze limit theorem. And the last one here, which is to graph the function. So we're trying to find the limit as x goes to -infinity of e to the x divided by x squared. So I have a picture here of the formula of the function. This is a graph. I got it from Desmos.com. We've got y equals e to the x divided by x squared. Now we want to know the limit. So we want to know the limit as x goes to -infinity, e to the x over x squared. So what we do is we just say, well, what's happening as x is approaching -infinity, right? It looks like our graph is approaching 0. So just by looking at this visually, we're able to see that this limit is equal to 0. We now have a new technique. That's the point of this video, is to introduce a new technique, which is, now that we know how to take derivatives, we can apply L'Hopital's rule. So here's the situation with L'Hopital's rule. If you're taking the limit, and your limit is, you get an indeterminate form, 0 over 0, right? Or some combination of plus infinity over minus infinity. Then, and this is a limit as x approaches a. A could be a real number. So a can be any real number. A can also be positive infinity. A can be negative infinity.
It's 8:15.
So we're talking about infinite limits. We're talking about regular limits. Okay. L'Hopital's rule says that your original limit is equal to the limit of the ratio of the derivatives. Okay. So let's go ahead and get started applying this. Let's see how it applies. So we've got this limit as x approaches 0 of sine x over x, and we've seen about 3 different explanations of why this is equal to 1. One approach was using the graphs, right? Another approach is using linear approximations. And now we're going to see the third approach, which is going to be using L'Hopital's rule. So we keep going. This example keeps showing up again and again because it's really important. So in this case, our f of x is going to equal the numerator. So f of x is going to be sine x. And g of x is the denominator, which is x. Okay. So f of x, as a is equal to 0. Let's put that here. A equals 0. Okay. So now, so we say f of x goes to 0 as x goes to 0, and g of x approaches 0 as x goes to 0. So we're in this situation right here, where we've got the limit as x goes to a has this indeterminate form of 0 over 0. Okay, so what we need to do is we're going to now look at f prime of x and g prime of x. So f of x is sine x, so f prime of x is going to be cosine of x. G of x equals x, g prime of x equals 1. So L'Hopital's rule says that the limit as x approaches 0 of sine x over x is the same as the limit as x approaches 0 of cosine x over 1. Okay, and now we can say, what's the limit as x approaches 0 of cosine x? Well, cosine x goes to 1, so this is going to go to 1 as x goes to 0. So this limit must be equal to 1 over 1, which is equal to 1. So that's how we get this one. Let's do another example. So here, the limit as t approaches 1. Let's see here. So our f of x is going to be the numerator, or actually f of t is going to be 5t to the fourth minus 4t squared minus 1. G of t is equal to 10 minus t minus 9t cubed. Now f of t goes to what as t goes to 1? Well, let's just plug it in here. So as t goes to 1, that's going to go to 5. That's going to go to 4. Okay. And then, so yes, we'll get 0. F of t goes to 0. And what about g of t? G of t, now as t goes to 1, this is going to go to 9. That's going to go to 1. So we'll have 10 minus 1 minus 9. G of t goes to 0 as t goes to 1. So what do we need to do? We need to look at f prime and g prime, right? So let's go ahead and we can compute our f prime of t is equal to, we had 5t to the fourth, so we'll have 20t cubed minus, what is that, 8t. And then g prime of t is going to be equal to negative 1 minus 27t squared. Okay, so the limit as t approaches 1 of f of t over g of t is equal to the limit as t approaches 1 of f prime of t over g prime of t, which is going to be equal to the limit as t approaches 1 of 20t cubed minus 8t over negative 1 minus 27t squared. Now as t approaches 1, the numerator is going to be 20 minus 8, which is 12, and the denominator is going to be negative 28. Okay, so that's our answer. And let's go ahead and write it up here. Negative 12 over 28, which I think we can simplify that. So 12 over 28, negative 12 over 28, negative 6 over 14, negative 3 over 7. Okay, so this is equal to negative 3 over 7. All right, and let's look at this last one here. So for the last one, the numerator is going to go to plus infinity as x goes to plus infinity, and the denominator also goes to plus infinity. So we're of this form over here, right? This is our indeterminate form, is plus infinity over plus infinity. So my f of x equals e to the x, g of x equals x squared. F prime of x is equal to e to the x, g prime of x is equal to 2x. So let's go ahead. Let me add a piece of paper afterwards. Add a page below. So we're saying the limit as x approaches plus infinity of e to the x over x squared is equal to the limit as x approaches plus infinity of e to the x over 2x, right? Because we have an indeterminate form of plus infinity over plus infinity. But now look, this numerator still goes to plus infinity. This denominator still goes to plus infinity. So we need to apply L'Hopital's again. So now our new f of x is equal to e to the x, and our new g of x is equal to 2x. So g prime of x is going to be 2, f prime of x is going to be e to the x. Okay, so we've got that this limit is equal to limit x goes to infinity. We need the derivative of the numerator, which is going to be e to the x, derivative of the denominator, which is going to be 2, right? And now let's look at our limits. So now the numerator is going to plus infinity. The denominator is just going to 2. So this limit is going to equal plus infinity. Okay, so our original limit is equal to plus infinity, and the main point of this example is to show that sometimes you have to apply L'Hopital's rule more than once in order to get your limit. Okay. Let's look at this fourth one here. So for 4, we've immediately got a problem. So let's look here. Now we want the limit as x goes to plus infinity, right? So the x is going to be going, as x goes to 0 from the right. So x is going to be going to 0. Natural log of x is going to approach negative infinity. So our indeterminate form is zero times negative infinity. This is not one of the forms that's listed in L'Hopital's rule. It's supposed to be 0 over 0 or plus infinity, plus or minus infinity divided by plus or minus infinity. What do? We need to let me actually just copy this. What we need to do is we need to rearrange our limit so that we can apply L'Hopital's rule. So here's our number 4. Okay, so we need to rearrange x, natural log of x, so that we can apply L'Hopital's rule. So the idea, here's the overall idea, right, is that if we look at this, so we said x is going to 0, right? So if x is going to 0, then 1 over x is going to be going to infinity. So let's take x times ln x and rewrite it as ln x divided by 1 over x. So check right now and make sure you understand why x is equal to 1 over x. Okay? So make sure you understand why. So now it's just algebra. Verify it for yourself. Now what we're doing here is we are rewriting x ln of x as, instead of x, we've got 1 over x, and then we still have our ln of x over here times ln of x. And now we're just going to rewrite this as ln x in the numerator and 1 over x in the denominator. The reason why we did that is because now as x approaches 0 from the right, so as x approaches 0 from the right, ln x is going to approach negative infinity. 1 over x is going to approach positive infinity. Okay, so we have our indeterminate form of negative infinity over positive infinity. And we can now apply L'Hopital's rule. So now let's apply L'Hopital's rule to the limit that we have. So the limit as x approaches 0 from the right of x ln x is equal to the limit as x approaches 0 from the right of natural log x over 1 over x. Okay, this is just from algebra. So let me just make that clear. So this step here is just algebra. And now this is equal to the limit as x approaches 0 from the right, and we need the derivative of natural log of x divided by the derivative of 1 over x. This step is true from L'Hopital's rule. So I just put L-H for L'Hopital. So what do we need to do? We need to get cracking with computing our derivatives. Okay, so I'm going to go over here in the corner and say, what is ln x prime? Well, the derivative of natural log of x is just going to be 1 over x. And now what about 1 over x prime? Now that I'm just going to rewrite it as x to the negative 1, the derivative of x to the negative 1. Now I can use my power rule to get negative x to the negative 2. Okay, so my limit is going to be equal to limit as x approaches 0 from the right. In the numerator, I've got 1 over x. And in the denominator, I have negative 1 over x squared. So now what am I going to do? I'm going to simplify. So I'm going to multiply the top and the bottom by x squared. Right? So I'm just multiplying by x squared. So now on the top, I'm going to have, in the numerator, I'll have x squared over x, which is just going to leave me with x. And in the denominator, I'll have negative 1 over x squared times x squared, so I have negative 1. Okay, so this is just equal to limit as x approaches 0 from the right of negative x, which is just going to be equal to 0. Okay, so now let's just go back and show the steps. So the first equality here was due to algebra, and we needed to rewrite our function so that it's in a form where we can apply L'Hopital's rule. And then we applied L'Hopital's rule. Now we took derivatives. So took derivatives, right? We just went over here, took those derivatives and, put them back in, inserted them. Then we just simplified. So this is to simplify, right?
It's 8:30.
And then once we simplified, we did some more simplifying. And then we just took the limit. Take limit. Okay? So our overall answer is that that limit is equal to 0. Okay, so let's do another problem here. This is x ln x, and this is the limit as x goes to 0 from the left. Okay. So now as x goes to 0 from the left, we still have the same function, which is x ln x. So I'm going to do pretty much the same thing that I did before. So let me actually just copy. Okay, it's taking too long to copy. So what I'm going to say is this limit, as we approach from the left, we're still going to do the same thing where we rewrite x ln x. So we'll have the limit as x approaches 0 from the left, ln x divided by 1 over x, which is equal to, now I'm going to do L'Hopital's rule. So I'm going to take the derivative of the numerator, 1 over x, derivative of the denominator, negative 1 over x squared. And I'm going to simplify. Multiply the top and the bottom by x squared, and I get x over negative 1. So I get limit x goes to 0 from the right of negative x. And the limit as you approach 0 from the left or the right is going to be equal to 0. Right? Because if I draw y equals negative x, it's just, well, it should be going through the origin, right? So it's just a straight line. So it doesn't matter if I'm approaching from the left or the right. I'm still going to end up with 0 as my limit, okay? So if this is my line y equals negative x, then as x is approaching 0 from the left or from the right, y is still approaching 0. So my answer is still 0. Okay, now let's look at this this problem down here. Limit as x approaches negative infinity of x e to the negative x. So now, as x approaches negative infinity, what's going to happen to x? X is going to approach negative infinity. E to the x is going to approach 0. So remember your graph of e to the x looks like this, right? And as x is approaching negative infinity, e to the x is approaching 0. My indeterminate form is negative infinity times 0, right? So I've got this form, negative infinity times 0. So what I'm going to do is I'm going to do the same trick that I did before, where I divide, where I rewrite my function. So x e to the x, we're going to rewrite it. X goes to negative infinity, e to the x over 1 over x. Now when I take the derivative, I'm going to take the derivative. I'm doing L'Hopital's rule. So it's equal to the limit as x goes to negative infinity. The numerator derivative is going to be e to the x. Let me put here L'Hopital's rule. And for the denominator, instead of 1 over x, I'm going to have negative 1 over x squared, right? Because 1 over x, the derivative of that is, equal to negative 1 over x squared, which is the same thing as negative x to the negative 2. Now, my e to the x, this is still approaching 0. My denominator is still going to be approaching 0. So I have the form 0 over 0. So I need to do L'Hopital again. So I say equals, and I'm going to do L'Hopital's rule again. Limit as x goes to negative infinity. The derivative of the numerator is e to the x. What about the denominator? So if I have negative x to the negative 2, and I want to take the derivative of that, I'm going to get 2x to the negative 3, right, which is 2 over x cubed. So I have 2 over x cubed, okay? And when I take the limit, the numerator is going to be going to 0 as x goes to negative infinity. The denominator is also going to be going to 0. So I don't know if you've noticed by now that each time that we apply L'Hopital's rule, our function is getting more and more complicated, right? And we continue to have the same indeterminate form, 0 over 0, 0 over 0. Things aren't simplifying. Look back at this case where we had to do L'Hopital's rule twice. Over here, we started off with e to the x over x squared. We took L'Hopital's rule and the x squared became simplified. It became 2x, right? And then 2x became simplified to just 2. And so we were able to come to some conclusion. Here, we're having, right, 1 over x, negative 1 over x squared, 2 over x cubed. Our denominator is getting worse and worse, right? So what does this mean? This means that we need to try something else. So instead of rewriting it, so here's how we rewrote it. Was the limit as x approaches negative infinity, x e to the x. We put the x in the denominator, Now we're going to put the e to the x in the denominator. So this limit, as x approaches negative infinity, x e to the x, is going to be the same thing as the limit as x approaches negative infinity, x, and in the denominator, e to the negative x. Okay, so this is just algebra. This part right here is algebra, because e to the x is the same thing as 1 over e to the x, right? Which is the same thing as 1 over e to the negative x. Okay. Now we're going to apply L'Hopital's rule. And we'll get this is the same thing as the limit as x goes to negative infinity. What's the derivative of the numerator? 1. The derivative of the denominator? Negative e to the negative x. Okay, so this is L'Hopital's rule. And now I am able to say that as x goes to negative infinity, 1 is going to go to 1. And what's going to happen to negative e to the negative x? Well, if e to the x looks like this, y equals e to the x, then y equals e to the negative x is the same graph reflected over the y-axis. Okay, and so what happens with as x goes to negative infinity, e to the negative x goes to plus infinity. So e to the negative x is going to go to plus infinity. So since our denominator is getting really large and our numerator is staying constant at 1, this limit is going to be equal to 0. There we go. So I hope as you're doing these problems, you're recognizing how important it is to have your basic functions, the graphs of your basic functions, either memorized or on a convenient cheat sheet, and to be able to do the transformations, right? So how do we get from e to the x to e to the negative x? You got to know that you need to flip the graph over the y-axis, okay? And the same thing, y equals negative x, you got to be okay with just graphing that automatically. Okay, and I think natural log of x we also graphed. Now, e to the x over x squared, this, we use Desmos, okay? This could be an interesting problem to do if the problem is graph y equals e to the x over x squared. I think we did something similar to this in class, where you're going to look at your first derivative, your second derivative, figure out where it's concave, where does it have asymptotes, where is it increasing, decreasing, intercepts. So it'd be a good problem if that's the goal of the problem, is to just graph the function. If you're trying to find your limits, then you want to have, just your basic functions, e to the x, absolute value, x squared, x cubed, square root of x. These are the graphs that you want to be very familiar with. Okay, so let's do 7. Now 7 introduces, or let me say 4, 5, and 6, I think. 1, 2, 3. So for problems 4, 5, and 6, you'll notice what they had in common is they were of the form something like 0 times plus or minus infinity, right? So that's what we had here, that's what we had here, and that's what we have here. So the key, if you have 0 times plus or minus infinity, is to figure out how to divide them, right? So that it becomes something like infinity over 1 over 0, or 0 over 1 over infinity, right? Because this will now turn into 0 over 0, so you can apply L'Hopital's rule, and this one turns into infinity over infinity, so you can apply L'Hopital's rule. So that's the point of these last 3 exercises, is to show you how to change certain indeterminate forms into something you can use. Let's do it with these last 3, or these, at least this one right here. So with number 7, here's what we've got. We've got a situation where as x goes to plus infinity, x to the 1 over x, let's see here. So this exponent 1 over x is going to go to 0, right? And the x is just going to go to plus infinity. So we've got an indeterminate form of infinity to the 0. This is our indeterminate form. Notice that this is not the form that we need in order to apply L'Hopital's rule, because L'Hopital's rule requires 0 over 0 or infinity over infinity. Here's how you change the infinity to 0 into something we can use. So our step is going to be to rewrite. So the key is going to be to rewrite x to the 1 over x is the same thing as e to the log of x to the 1 over x. Okay? Because remember, e and log are inverses of each other. Now we can rewrite this as e. We can use the properties of log to take that 1 over x and bring it downstairs. So we'll have e to the 1 over x times log x. And now if we look at this exponent, 1 over x times log x, as x goes to infinity, log x goes to plus infinity, and 1 over x goes to 0. This is as x goes to plus infinity. But wait, what if we rewrite it as log x over x? Then the numerator goes to plus infinity, and the denominator goes to plus infinity. So we can apply L'Hopital's rule to the exponent. And that's what we're going to do. So we're going to say step 1. So step 1 is to rewrite like so. So we'll say x to the 1 over x is equal to e to the log x over x. Okay? So remember that exponent 1 over x times log x is the same as log x over x. So that's our step 1. Step 2 is going to be to figure out, calculate the limit as x goes to infinity of the exponent, which is log x over x. Log x over x. Now this should be pretty simple because we can just use L'Hopital's rule, and in one step we can calculate this is equal to. Now why can we use L'Hopital's rule? Perhaps I went over that a little too quickly. As x goes to infinity, the denominator is going to go to plus infinity, and the numerator is going to go to plus infinity. So we have the indeterminate form of infinity over infinity, which is what we need. So I'm going to apply L'Hopital's rule, which means take the derivative of the numerator, which is going to be 1 over x, and take the derivative.
It's 8:45.
Thank you. Take the derivative of the denominator. The denominator is going to be 1, right? We can just rewrite this as a limit as x goes to infinity. This is just 1 over x. And now as x goes to infinity, what happens to 1 over x? It just goes to 0, right? So it goes to 0. So now step 3 is we are using limit laws. Use limit laws to say to conclude that if we have e to the log x over x, and if log x over x goes to 0, then e to the log x over x is going to go to e to the 0, which is 1. All right, so since e to the x is continuous, if we want to know the limit as x approaches infinity of e to the log x over x, it's just e to the limit as x approaches infinity log x over x. Okay, so our final answer is going to be equal to 1. And also note that here when I've written log x, that is the same thing as ln x. Okay, so I don't mean like log base 10. Okay, let's do another. I'd like to open up a new sheet here so I can have space. Cut. Let's add a page below. Paste. Okay, so let's do number 8. So for number 8, let's check that we can apply L'Hopital's rule. So as x goes to 0, what happens to the numerator? E to the x minus 1 minus x goes to, well, let's look and see. So as x goes to 0, e to the x is going to go to 1, right? And then x is going to go to 0, so we'll have 1 minus 1, right? That'll be 1. So 1 minus 1 minus 0. So this numerator is going to go to 0. And what about the denominator? X squared, of course, is going to go to 0. So we have our indeterminate form of 0 over 0. And let's apply L'Hopital. So L'Hopital's rule. So the limit is x goes to 0, e to the x minus 1 minus x over x squared equals, and this is due to L'Hopital's rule, the limit x goes to 0. I need the derivative of the numerator, e to the x minus 1, divided by the derivative of the denominator, 2x. So now let's check. Let's see here. So as x goes to 0, the numerator is going to go to, so as x goes to 0, the numerator is going to go to 0, right? Because e to the x is going to go to, that's going to go to 1. So I have 1 minus 1, which is 0. And the denominator, 2x, is going to go to 0. So we've got indeterminate form, and we can apply L'Hopital's rule again. You can say this is equal to, and this is according to L'Hopital's rule, equal to the limit as x approaches 0. Now I need the derivative of the numerator, which is e to the x, and the derivative of the denominator, which is 2. And now, as x goes to 0, the numerator, e to the x, is going to go to 1, and the denominator is just going to stay at 2. So this limit is going to be equal to, this limit is equal to 1/2. Okay, so that's our final answer, is that this is equal to 1/2. Okay. Now let's go to this one right here, which is 9. Number 9. So in order to do number 9, first thing we're going to do is we're going to say what happens as t goes to 0. So as t approaches 0, 8 to the t minus 5 to the t approaches what? Well, first thing I'm going to do is 8 to the t, that's going to approach 8 to the 0, right? It's going to go to 8 to the 0, which is 1. And then 5 to the t also is going to go to 1. So our numerator is going to go to 0. And then our denominator, right, our denominator, which is t, is going to go to 0. So we've got an indeterminate form of 0 over 0, and we can apply L'Hopital's rule. So applying L'Hopital's rule, we get that the limit as t goes to 0, 8 to the t minus 5 to the t over t is equal, according to L'Hopital's rule, to the limit as t goes to 0. Now, what is the derivative of the numerator? Well, we need to know what is the derivative of 8 to the t. So that would be log 8 times 8 to the t. And the derivative of 5 to the t is going to be log 5 times 5 to the t. The derivative of the denominator is going to be 1. So let's see now what happens as t goes to 0. So as t goes to 0, this is going to 1, as we said before. 5 to the t is approaching 1. So this limit is going to be equal to log 8 minus log 5 over 1, right, which is just the same thing as log 8 minus log 5. Okay, so what's tricky about this problem? You have to remember the formula for the derivative of a to the t. So in general, a to the t d dt. The derivative with respect to t is going to be log a times a to the t. Okay, so we've got 3 problems left, and let's start with so let's just start with this first one here. So we've got the limit as x approaches 0 of sinh x minus x over x cubed. The issue here is, what is sinh x? So if you recall, sinh x is the same as e to the x minus e to the minus x over 2. So what is the limit as x goes to 0 of sinh x? Okay, well now as x goes to 0, e to the x is going to go to 1, e to the negative x is going to go to 1, so sinh x is going to go to 0, right? So this means that sinh x is going to, so let's see here, so as x approaches 0, sinh x minus x approaches 0, right? Because sinh x is going to 0 and x is going to 0. So the numerator approaches 0 and the denominator, of course, is going to approach 0. So we've got an indeterminate form of 0 over 0, and we need to apply L'Hopital's rule. Okay. So in applying L'Hopital's rule, we're going to say that the limit as x approaches 0 of sinh x minus x over x cubed is equal to the limit as x approaches 0. Now we need the derivative of sinh x. What is the derivative of sinh x? Well, so we've got this 1/2, right? We've got a factor of 1/2, so that stays the same. What's the derivative of e to the x? That'll just be e to the x. What's the derivative of e to the negative x? That'll be negative e to the x. So this is actually equal to cosh of x. So we'll have cosh of x minus 1 over 3x squared. Now what happens as x goes to 0 to cosh of x? So as x goes to 0, e to the x is going to go to 1. That's going to go to 1. So cosh of x is going to go to 2 over 2, which is 1. So cosh x goes to 1. So we have an indeterminate form of 0 over 0, right? So we can apply L'Hopital's rule again. So say this is equal to, according to L'Hopital's rule, the limit as x goes to 0. Now we need the derivative of cosh. And what is the derivative of cosh of x? I made a mistake. This should be e to the x plus e to the negative x. So that when we take the derivative of cosh, we get sinh. So this will be sinh of x, and then the minus 1, the derivative of a constant is 0, divided by 6x. Now sinh x, as we said before, approaches 0, right? And as x approaches 0, so we've got indeterminate form again. So we can apply L'Hopital's rule. Notice that our denominators are actually getting better. Okay, so we start off with x cubed, then we got 3x squared. Now we're at 6x, and one last time it's going to do it for us. So we'll have the limit as x goes to 0. What's the derivative of sinh? It is cosh, so cosh x over 6. And now we said before that cosh is going to go to, cosh x goes to 1 as x goes to 0. So this limit is equal to 1/6. So the difficult thing here, I guess, is applying L'Hopital's rule several times and remembering that sinh x is e to the x minus e to the negative x. Okay. So this next problem, is a We say it's a classic type of problem because when you as x goes to infinity, 1 plus 2 over x approaches 1, and the x approaches infinity. So we've got the indeterminate form of 1 to infinity. Okay. Now, we saw an example of how to deal with this before. So when you have an indeterminate form like this, what you do is you rewrite your function. So we're going to start by rewriting 1 plus 2 over x to the x. We rewrite it as e to the log, or let me see here, we can put natural log. E to the natural log of 1 plus 2 over x to the x. Okay? And then the x we can bring down using our properties of logs. So I have e to the x times the natural log of 1 plus 2 over x. Okay? So this is our step 1, is to rewrite. Now step 2 is to calculate the limit. Since we're looking for the limit as x approaches infinity, we need the limit as x approaches infinity of the exponent, x times natural log 1 plus 2 over x. Now, as x goes to plus infinity, this is going to go to plus infinity, and natural log, so this is the 2 over x is going to go to 0, and natural log of 1 is 0, so all of this goes to 0. So we have the form of infinity times 0. What we're going to do, we're going to rewrite it dividing by the x. So when we rewrite it, we'll have natural log of 1 plus 2 over x divided by 1 over x. Now we're ready to use L'Hopital's rule, okay, which is equal to, so we need the limit as x goes to infinity. The derivative of the numerator. What is the derivative of the numerator? It's going to be, so maybe we do a little side bubble. So we have the natural log of 1 plus 2 over x. We need the derivative. This is definitely chain rule. So we'll have 1 over the inside, which is 1 plus 2 over x, times the derivative of the inside, which is going to be, what is the inside? The inside is 1 plus, so it's 1 plus 2 over x. We need the derivative of that, So we'll have 1 over 1 plus 2 over x times, this is 2x to the negative 1, so we'll have negative 2x to the negative 2. Okay, so that's what I'm going to put in as my new numerator.
It's 9 hours.
So I have 1 over 1 plus 2 over x times negative 2x to the negative 2. For my new denominator, I need the derivative of x to the of 1 over x, which is just going to be, so we can go over here, d dx of 1 over